All right, everyone, we're going to talk about the independent samples t-test. You use the independent samples t-test when you want to compare two sample means, and it's a between subjects design, different people into different conditions. We call it independent because the observations in the different conditions are independent of each other. Our first step is to apply the mad outlier detector. We can check for normality as well in our own data, but not for homework. Our first step is to state your null. And I'm just simplifying it. You now understand what the null is. You proved that to me in class, so we just have to state it one way. I am trying to statistically disprove that the population mean from condition 1 minus the population mean from condition 2 equals 0. Now, this is the inferential part. We're trying to infer population means from sample data. So that's why we use mu here. I think you got that, but I wasn't sure. So step number 2 is we're going to have to gather all known population values in simple sample descriptive statistics. So we got two means, we have two standard deviations, we have a mean difference, we have two n's, we have 2 degrees of freedom, which is just the n minus 1 of each group, and we do have a total degrees of freedom too, which is just the summary of that. What I'm going to wait in this video till the end to go through one problem with you, because while I'm going to do all these steps, I'm going to run SPSS first, just so I can get all this data without having to calculate it in Excel. So now step number 3 is calculate and interpret the most important descriptive statistic, Cohen's d. And you can see it's basically the same formula, except now we have 2 standard deviations that we have to pool across. And if you see it here, you see there's a very complicated formula proven by math nerds to be valid. Essentially, it's a weighted average of standard deviations weighted on degrees of freedom, not n per group. But you can see there, it's a standard deviation formula. We can tell that with the square. And it's weighted degrees of freedom of group 1 times the standard deviation of group 1 plus the degrees of freedom of group 2 times the standard deviation of group 2 plus the degrees of freedom of group 1 plus the degrees of freedom of group 2. You can see me work through that problem here. And I'm pointing out, like you can see it in the slide, this is where it just becomes ridiculous to do these calculations by hand. You will mess this up every single time, and you're going to see this pattern now where before you were like okay and comfortable doing the equations by hand, but now you're just kind of probably like I am, like this is ridiculous. This is just not helping me understand what I'm doing. This is math nerds doing better math for us, but our goal isn't a quantitative psychology class. This is really, a class on how to be effective and efficient at data analysis. So there's the formula, but I'm going to show you I found a beautiful tool for Cohen's d. You're gonna love this, but I'll show you that at the end of the lecture when I start a whole problem. Everything's the same here. Our random sampling distribution of mean differences is essentially, the same thing. We still got to draw it. It's T-shaped. Limits are negative and positive infinity. The mean difference is 0. Standard deviation is called standard error, right? We still have degrees of freedom, but now we have 2 specific degrees of freedom. How many observations, numbers in this condition, are hypothetically free to be any number and still average to the sample mean, right? How many observations, numbers in the other condition are hypothetically free to be any number and still average to the sample mean? Let's add them together, and you get the total n, all the participants in your study minus 2. But it's literally, that's it. That's all degrees of freedom is. It's this hypothetical, if all the numbers in your sample mean had to average to your sample mean, riddle me this. How many of them are free to vary? Well, it's n minus 1 in group 1, n minus 2 in group 2. We can look, our degrees of freedom change our t-distribution. We can see that. So does the standard error of the distribution. That changes it as well. And now I left the standard deviation off of there, but now we have another calculation where I'm using my pooled standard deviation from Cohen's d squared 1 over n1 plus 1 over n2. What is this? Is this the formula for time travel? This is another thing that it's still, we know what it is, but because math nerds, we have to calculate it in a different way, and it's more complicated because you have like 2 standard deviations, 2 n's, all this fun stuff. So clearly, I want you to see this formula. I don't need you to use this formula, not for me. There's no reason to. I don't use these formulas when I do my data analysis. I let the computer do that, and that's what we need to get proficient at: data analysis, not 1950s math. Okay, so like you can see right here now we just got a little bit harder, and we have even more harder tests to learn. We go up 1 level in difficulty, and the equations go from kind of interpretable to completely uninterpretable. This is the equation for time travel, if I'm looking at it. Okay, you can watch me walk through that math and find my standard error. But honestly, at the end of the day, I don't want you spending your mental energy doing these calculations. I want you to spend your mental energy thinking about what we're trying to solve, which is this problem right here. We're trying to figure out what our sampled p-value is. Okay, so we put our sample means on the problem. We identify the area of P. I'm putting the degrees of freedom and the standard error on this problem just because that determines the shape. I'm not making you change the shape. This bell-shaped pizza is a bell-shaped pizza. We got to calculate our test statistic, and because we already calculated standard error, it's not that bad. The mean, in this case, we take mean 1 minus mean 2, mean control minus mean empathy. That equals 3.9 divided by 0.79. That equals 4.94. And again, the same things still hold. It's basically a Cohen's d for our hypothetical distribution where the null is true. Our means are 4.94 standard errors apart. Right, very similar to Cohen's d. Signal, a different measure of signal to noise ratio is 4.94. Everything is signal to noise in statistics. So that's the same essentially. We find our p-value, or we're trying to, we know we're trying to find our p-value. I'm putting my known t-scores on the distribution. So I'm seeing in the original scores of the means and in t-scores, I've just added another number line. We're going to solve for p, which I can use the table. I'll show you how to use that again. Use SPSS, use PSPP, use my fancy. There's actually another thing we can use that I'll show you. It's the Cohen's d calculator will do it for you as well. And because we just entered a more complicated world, I'm going to do one problem completely at the end. I'm not inserting all the steps in the middle. I'm just going to do it at the end. We find our p-value, or we're trying to, we know we're trying to find our p-value. Interpret my p-value, same steps. Have I statistically disproven the null hypothesis? Rejected it, right? Yes. In this case, yes. If my p is greater than 0.05, I don't know anything. We're going, yep, I have an Excel maker. I'll show you. I have a new one. You're just going to be plug and shove. All right, so now we get to write up our results. And I took that writing from Daniel Lackins and I converted it to what I needed. So Group 1 scored higher than Group 2, became participants assigned to the empathy intervention showed less racial bias, and participants assigned to the control condition. If you notice, I took what he gave me and made it better, made it easily interpretable for my audience, and then I insert my statistics, my mean, my standard deviations, my t with degrees of freedom, my t-score, my p-value, my 95% confidence interval, my Cohen's d, and a 95% confidence interval of my Cohen's d, which I will show you how to calculate, but that is very interesting. You don't have to include the 95% confidence interval of the Cohen's d. However, it makes life easier. I have a massive effect and a massive effect, right? Those are Cohen's d's. So my worst case scenario, it's a massive effect. My best case scenario, it's a massive effect. That's a little bit easier to interpret than my mean difference. My worst case scenario, my mean difference is 1.49. My best case scenario, my mean difference is 2.94, right? It's a little bit easier to interpret it when it's converted to a Cohen's d. So I am going to work through this problem right now using all our tools. I know some people get overwhelmed by this because I use all the tools possible. You don't have to use all the tools. One thing that is important in my videos that follows, you'll see a Levene's test for equality of variance. If that is significant, you have to use the bottom t-score value. You'll see it, okay? Just keep that in mind because I don't mention it in the videos. But right now I'm going to solve this problem. This is my dissertation work. I had, participants, nursing students, going for their PhDs with like 8 years of nursing experience. Either they were exposed to an empathy intervention where they were just asked to imagine how another's pain affected their life, or they were in a control condition where I told them to try their best. So here's some simulated data that represents the results that I found. They're a little better than what I found, but they're in the same direction. But ultimately, I'm going to walk through this problem step by step. First, I'm going to use SPSS, and that's where I forget to tell you about the Levene's test for equality of variance because it was non-significant. Then I use PSPP. Then I use some other tools along the way, but you'll see it in a second because it's starting now. All right, so what you're going to see that follows is I keep going back to my PowerPoint, and I keep talking about my PowerPoint as if it were my homework, but I don't make that clear. Well, when I was doing that, I realized, that could confuse students. How could I get students to really just follow the instructions and have an easier way of answering these problems? So I just created a Word document with all these steps on it. Step 0, check for outliers with MAD. Step 1, state your null as a mean difference. Step number 2, give me your simple sample descriptive statistics, your means, your standard deviations, all that stuff that's on my slide. You'll get it from your PSPP output. Cohen's d from Lackins' Excel file. Draw your random sampling distribution of mean differences curve if the null were true. I didn't really go over it that well in the lecture because you should know this by now, but if not, if that doesn't make sense, come talk to me. And you draw your p-value problem on there. So you just draw your curve, draw the middle's going to be 0, negative infinity, positive infinity. Put your mean difference on there, and we'll be fine. That's all you really need for that. Calculate your test value, go to SPSS or PSPP. Calculate your p-value, just write it in there. Do you disprove and reject the null? Write it in there. Step number 8, graphs, you can paste those in there. Step number 9, paste your write-up in there. And that's really it. Okay, but this will help you organize your steps, and in the future I'm going to use this document to create my own answers when I'm answering my questions, because I do realize with the amount of tools that I'm using, students are getting a little lost. But ultimately, check for outliers, just write check. Then state your null as a mean difference. mu1 minus mu2 equals 0, but give me subscripts for 1 and 2. Sample descriptive statistics, really means, standard deviations, ends, and degrees of freedom. Cohen's d's, get that from the Lackins file. Draw your curve, and your p-value problems, you got to draw your curve. You got to put the middle at 0, negative infinity, positive infinity. Your sample mean, put it on the correct side. Draw the mirror image of it. Shade in your p-values. That's all I want there. You don't have to do all the fun stuff when you calculate t. You don't have to do that. You just have to set up the problem. I do that to show you how it all works out. Step number 5, calculate your test with PSPP and SPSS. Step number 6, just type it in there. Step number 6, p-value with SPSS, type it in there. Disprove or reject or retain, whatever, doesn't matter. Write it in there. Graphs, paste them in there. Paste your write-up in there. Copy the write-up that I gave you. Put your write-up in there and give me the answers, okay? So use this tool for your problem at the end of the homework. So I've already set up my variable view, but I want to show you how I did that. I like to always make my first row of data, or my first column of data, my participant number. Then I like to make the next one my independent variable and the final one my dependent variable. Participant number is not so important for this specific test, the independent samples t-test, but it is important for the dependent samples t-test, and you'll see that in our next lecture. But I might as well just start doing it now. Do you have to put in your participant? No, you don't. I'm not going to take off for it. I'm just going to do it. At the same rate, I have my empathy condition, and I know they teach you all the values in how to enter those in the lab, and so I've already entered mine. I put in a value of 1, put the name control as the label, and hit add to empathy add. That's all I did there. But now I know 1's a control and 2's empathy. And then I have my racial bias pain treatment. You'll probably notice that my variable names are often really long, and that's just because I'm always scared that when I go back to my data, I'm not going to know what anything is, right? So I don't want to go back in 5 years and not know what things mean. So now I have all my variables set up, and I'm going to my data view, and it's time for me to enter in my data. And so I pull it up, and I'm like, okay, participant 1 is in the empathy condition, and they scored a 0. Participant 2 is in the empathy condition, and they scored a 1. Participant 3 is in the empathy condition, and they scored a 0. Participant 4 is in the empathy condition, and they scored a 1. Participant 5 is in the empathy condition, and they scored a 0, because that's this one right here. 6, empathy, 0. 1, 2, 3, 4, 5, 6. 7, empathy, 1. 8, empathy, 1. Now we have participant 9, 10, 11, 12, 13, 14, 15. So we have participant 9, control condition, and they scored a 2 on racial bias. So participant 10, they were in the control condition. They scored a 3 on racial bias. Participant 11, control condition 2. Participant 12, control condition 2. Right? 2, 3, 2, 2, 2, 3, 2, 2, 3, 4, 3. So we got 13, condition 1, 3. 14, 3, 4, 3. Condition 1, 4. 15, condition 1, 3. So before I run my analyses in SPSS, I'm going to pull out the data per each condition and check for outliers. Now, you don't do it in terms of the entire data set because the two different conditions were treated differently. When you do that, you often hide outliers. It just makes sense to me to remove outliers per condition. So now I'm going into my MAD outlier detector. Go ahead and you can see I was practicing a little bit, but here we go. Oh, I copied the participant numbers. You are not supposed to do that. We all make mistakes. That was a minor one, so I'm not going to restart the video or anything. But yes, I copied in the wrong thing, and I noticed it real quick. But that's okay. We all make mistakes. You make mistakes. I make mistakes. What we notice here, though, no outliers. So thank you, no outliers. I don't have anything to do there. I'm deleting that. Going back into SPSS, grabbing my control condition scores, putting them in, getting ready to remove outliers. So control, copy. I'm putting them in. I click on the first box and hit Command V. That's what I'm doing. I could hit Control Paste. Just get them in there. You've been doing this for a little bit. And you see no outliers again. So now what I get to do is I'm gonna run my scores to get my t-test results. but this is because it gives me all the descriptive statistics that I need. So I don't want to do that in a separate program. I don't have to. So I'm just running this first, which you're like, oh, that's probably unusual, right? Well, yes, it is a little unusual, but ultimately it just makes everything so much easier. All right, so now I'm going to go analyze, compare means. Going into my independent samples. So I know you can't see what I'm doing. I'm up at the top here. I'm clicking. It's an analyze option. I clicked it. Another option, compare means, comes up. Then the independent samples t-test option comes up, and I click on it. Now you can see what I'm doing, and you can see I've already practiced this. So I'm going to remove everything. My racial bias and pain treatment, that's my IV. I'm going to define, oh wait, no, that's not my IV. What am I doing? Cancel. It's early, sorry y'all. That's my test variable, which is my dependent variable. And my independent variable is my grouping variable. Don't know why they have to call it different names, so just watch the video until you get proficient at this stuff and follow them along. And it's like group 1 is my control condition, group 2 is my empathy condition. I'm hitting continue. I'm clicking OK. And you're going to see here, I did this already once, so you caught me, but I'm going to just delete that if it'll let me. Used to let me delete these. Here you go. There, I just hit it. That'll work. Okay. So you're gonna come back to, you're doing this first, but you're gonna come back to it throughout the steps. You can see all my descriptive statistics that I need are here. My ends, my means, my standard deviations, not Cohen's D, but all my basic descriptive statistics are here. So let's go back to our slide, right? I grabbed our data and I'm just like, okay, just like you are, you're probably like step 0. Hey, he did that. Good on him. That's done. Step 1, state your null. I'm trying to statistically disprove the mu of, it's right here. This is it. So the mu of empathy on racial bias and pain treatment minus the mu of control on racial bias and pain treatment equals 0. Does it matter which one's first? No, it does not. It's a mean difference, so it doesn't matter. Then I'm going to gather all my known population values. So here I go back to my SPSS. I write in my control mean, my empathy mean, both standard deviations, my mean difference, my ends, and my degrees of freedom, which I'm just going to go back to the SPSS and I literally am like, oh, my mean for control is 2.71. Higher numbers are more racial bias. My mean for my empathy is 0.5. That's quite a difference. My standard deviations for each group is 0.7593, 0.53452. This standard error of the mean is for each group, okay? Don't worry about it too much because it's not what we use. But my degrees of freedom are going to be 6 and 7. So from here, I can fill out that complete table. You could probably make a nice table somewhere to enter the number in, nicer than I did. But the data is pretty simple here. Now here is the test. It's like, oh my Lord. Oh my. I am not doing this one by hand. I am not even doing this one by Excel, even though, I'm not teaching you to do it by Excel the way I used to just create the formula. You could create this formula in Excel and you're going to make a mistake. So I actually do have a statistical hero that I want to introduce you to. There you go. Daniel Lackins, who teaches one of the best advanced courses. This Coursera course is one of the best stats courses that is offered online. So like this, improving your statistical inferences. Let's see if they got an image of the guy. He's just this like super psych stats nerd guy that I kind of look up to. Well, he has written this paper on effect size that is amazing, okay? Calculating and reporting effect sizes in Frontiers in Psychology. And this is a primer. This is an advanced lesson in effect size, okay? I'm not going to have you read this paper, but if you really care to learn about everything of effect size, you have questions, here you go. It's all here. But what's great is that, like, my statistical hero has created a effect size calculator that is very, very, very easy to use. I'm going to upload this. First, I was playing around with just some cells, checking calculations and stuff. So essentially, what I have to do is I go into my SPSS output, right? And I get it up there so I can see it and enter in all my descriptive statistics into this great little program. My mean of group 1, well, that was my control group. My mean of group 1 is 2.7143. My standard deviation of group 1 is 0.75593. My N of group 1 is 7. My mean of group 2 is 0.5. My mean of group 2, my standard deviation of group 2 is 0.53452. My number of participants is 8. And what you can see here is it does all the calculations for you. The one thing I'm going to point out is that the t-test, well, I'm not going to point out anything about the t-test on this specific graph, except that I want you to see that the numbers here line up here, but the numbers here do not line up here. When I'll explain that later. But what's really cool, really cool is we have, our 95% confidence intervals of the mean difference. We have like all this amazing stuff. We have, but really what I wanted to see is this Cohen's D, the first one, the S. You'll have to read his paper to figure out what the D one is, the other one is. But, I see that my Cohen's D is 3.426. So now I have my Cohen's D by literally just plugging in my descriptive statistics into here, but I didn't show you all this stuff. So, okay, start. Is this a t-test? Yes. Is a comparison between correlated samples? That means dependent samples. He's from the Netherlands and he's a statistical nerd, so he's going to use a different word than we're going to use in intro, but it means dependent samples. Do you have the mean, standard deviation, R's, and, well, that's yes. No. Do you have the mean, standard deviations, and N's? Yes. We use the thing I used earlier, right? So it sent us there. That's how we got there. So I love this table, right? You just have to answer questions and know what you're answering. Is this a t-test? Yes. Is a comparison between correlated samples? No. Correlated samples is dependent samples. Do you have mean, standard deviations, S's and N's? Yes. Just enter the data in these green boxes or gray boxes. They look green to me, but they're green. The gray is the output. And then the great part is that you get your Cohen's D's. You get your Cohen's D, this first box right here. That's all you need. There are other measures of effect size, just so you know. That's no big deal. And here's another thing I want to point out. Look, when you all are saying like, oh, isn't that stealing? My statistical hero says, no, it's not stealing. This is how you should write out your data. Here's an example. Please steal my wording because I want you to write it correctly. One of my statistical heroes is telling you to do the same thing that I told you to do the other day. And you were like, isn't that cheating? No, it's not cheating. Not at all. Okay? No, it's just being a good, work smarter, not harder. Okay. So we now have our Cohen's D, which is 3.426. I'm going back here and I'm like, okay, I have found a massive effect. My control group, mean racial bias of insert the mean. I'm not looking at it right now, but I can go back there. My mean racial bias in my control group was 2.714. The mean with a standard deviation of I don't have to read that, but with and my mean of my empathy group in terms of racial bias was 0.5. These two means are 3.4 standard deviations apart. My signal is 3.4 times the size of my noise. This is almost a piece of evidence for physics, and of course it is because I made up the data. But essentially, we just interpret our Cohen's d just like we've been doing the whole time. I'm not going to write it out on the PowerPoint because I assume you're hearing me and following along. And I don't want to change my PowerPoint because it'll mess everything up. All right, so then I'm like, okay, step 4. Step 4 is actually super, super duper easy, right? I'm going through all this stuff. I'm basically getting down here, and I'm drawing my graph, right? I got my bell curve. I'm finding my mean difference. I'm going back to my SPSS. My mean difference was 2.21, right? I know that my control group was more racist, more prejudiced, than my empathy group, so I know that as well. I put in my mean differences on the graph. I put in my standard deviation of this distribution is standard error, and it's standard error of the difference, so it's this 0.3344. All right, I know that's what it's going to be. I still haven't calculated p-value yet, but SPSS gives me that value. My degrees of freedom, SPSS can give me as well. In this case, my degrees of freedom are 13, and we can see, does that make sense? So 7 plus 8 is 15, minus 2 is 13. In this 6, we're free to vary. In this 7, we're free to vary. 6 plus 7 is 13. So my degrees of freedom are 13. No big deal, right? So we're good there too. I throw those on my chart, no big deal. We're getting there, My test statistic, I'm going back to my SPSS. That's been calculated. We can see my test statistic here is a 6.621. So I'm going to go back here and put my 6.621. I'm going to, that's my 6.621, and I'm going to put that right here and here and here, just like before. These would have been changed. And solve for P. Well, we've done that. My P-value is, wow, tiny. I double-clicked on it to try to see if I could figure out how tiny it was. 0.000017. Okay. So I got a tiny effect. Great. I got a tiny p-value, but a large effect. So this is basically kind of how my dissertation worked out. So it was very nice to have that. But yeah, my p-value is super tiny, so I'm, less than 0.001 again. I don't really have to do much on that slide. I have statistically disproven the null hypothesis. I've rejected the null. I realize there's a probability that I may be wrong, but it's so tiny that 0.000017 becomes 0.00017 or whatever it was. You take 2 zeros off. Step 8, I'm going to use the Excel maker, and I'll show you that. I'm going to stop here, do the same, just go through the same steps in PSPP, and I'll pick this up. I'll pick up the graphs in a second. So now I'm just going to show you the PSPP part. I assume you can go through the Cohen's. I'm not going to redo the Cohen's d and stuff, but okay. So we have the same problem. It's basically the same program. So I write my name, participant. I'm using the cheap G.I. Joes here, so I have to hit enter after I type in my name. It doesn't just automatically do it for me. That's fine. My next variable, just like before, was empathy condition. So that might be the short empathy condition. Gotta hit enter. It's hard to go from SPSS to this sometimes. And then I go racial bias pain treatment. Right? I could do this. I could be like the neuroscientists. They have cool symbols. So there we go. I have all of our data in here, and it's the same thing. Participant 1, you got to hit enter every single time. Their empathy condition. Actually, I want to see it in the variable view if I can add labels. Yes, you can add labels. Let me see. Oh, okay. I'm not messing around with labels in this thing. Nope, nope, nope. This is just about getting my p-value. I'm quitting on that one because this is not, I'm just going to say my empathy condition is 2. Oh, gotta hit enter, right? Like it is frustrating. I totally feel you. And then my score is a 0. Now I'm getting better at hitting enter. Participant 2, enter. The empathy condition is 2, enter. Their score is 1, enter. Empathy condition is, I don't know why it's highlighting things, right? G.I. Joe, I guess. That's just what I'm going to go with. Empathy, my participant is 3. They're in the empathy condition. Their score is a 0. Participant 4, don't know why it's doing that. They're in the empathy condition. Their score is 1. Participant 5, they're in the empathy condition because that's 2, right? I didn't hit enter. And now I'm on 5. 1, 2, 3, 4, 5. So I got 0, 0, 1, 1. So 0. 6. Empathy conditions 2. Score of 0. 7. Enter. Empathy condition 2. Score of 0. I didn't hit enter, so I got to go back and hit enter. Thought I did. Participant 8. Ha! You all can laugh at me. You're going to enjoy this. 2. And then I have a 1. And I added 1 too many zeros. So I'm like, wait, there's only 1, 2, 3, 4, 5, 6, 7, 8. So now I got to check all my data because I messed up. 0, 1, 0, 1, 0, 0, 1, 1. So this one needs to be a 1. Enter. And it hates me. 1. Enter. Okay. Yeah, like sometimes just persist. Just persist. Participant number 9, enter. Condition 1, 2. I didn't hit enter again. What is wrong with your professor? What's he doing? It's not me. It's the G.I. Joe program. 10, enter. 1, enter. 3, enter. Yes, I did it that time. 11, 1, enter. 2, enter. 12, enter. 1, enter. 2, I think. Let me see here. 2, 3, 2, 2. Yes. Whew. 13, enter. 1, enter. 3, enter. 14, enter. 1, enter. 3, 4, enter. Participant 15. I didn't hit enter. I almost got it. 1, enter. 3, that's the hardest part. Oh, I'm so glad to be done with that. And then I click, I'm going to make it big. And then I'm going to make it big. I'm going to click analyze, compare means, independent samples t-test. It's the exact same. It's the exact same as SPSS, just a little less fun to use. My DV goes here. My empathy condition goes here. It does want me to define my groups. 1 and 2. Continue. Click OK. And then I'm going to have to get out of that and find wherever. Oh, it's right here. It's up here this time. The weird thing about PSPP is like sometimes you have no idea where you're, where it's outputting things, okay? But, one of the things that I didn't mention in the previous video, and I don't feel bad since we're doing 2, is one of the assumptions of a t-test is that the variances across the 2 groups are the same. So right here, if this Levine's test for equality of variances, a lot of students often mess that up and put that down as their t-statistic and their p-value. Don't do that. I'm going to talk about this output a little bit more. If these 2 numbers, they go together, they go together, nothing else goes with them. If this number is less than 0.05, you need to use the bottom row because equal variances are not assumed. I'm not going to talk too much about that. Just this is a test of equality of variances. If it's a significant test, that means the variances are different across your two groups, and you need to use the bottom row, okay? And you can see here that the degrees of freedom change. They're adjusted. The degrees of freedom are adjusted. All this stuff is going to impact our t-value, essentially. So here, again, we got our standard error of the difference. We got our t-score. We got our p-value. We got the mean difference, 95% confidence interval of the mean difference. Use the top row when this is greater than 0.05, when the Levene's test for equality of variance suggests that the variants are not different. Okay, when they suggest that the variances are different, you go to the bottom row. That is it. Now let's just go back to SPSS and make sure everything is the same. Everything's the same. It's the same as our Cohen's D calculator, which is amazing. So in today we've got great results. We've got things working out. I'm looking at them and they're the same, right? 6.62, 6.46, and I click on PSPP and you can see here I can actually line them up for you, right? You can see 6.62, 6.4, 13, 10.65. Can you click? You can't click on tables in PSPP. G.I. Joe. I'm going to say that every single time because every time I got one of those fake G.I. Joes when I was a kid, I was sad. But yes, it's a joke to me. It's only funny to me. I get it. Mean difference. This is our signal. A signal of our experiment. Standard error of the difference, 0.33. That goes on. That you just put that number on the graph. You also put the degrees of freedom of 13 on the graph. 90% confidence interval of the mean difference. Worst case scenario, my empathy intervention reduces racial bias by 1 point. Best case scenario, it reduces racial bias by 3 points. It's only a 7-point scale. This isn't bad. My worst case scenario is not bad. I definitely have an effect. I definitely have a reduction. And in this case, too, I know the effect's large because we looked at the effect size, so it's a large effect. But even if it were small, I'd say, well, shouldn't we be getting rid of even the smallest racial bias in pain treatment, right? Shouldn't we, morally, ethically? This is the case that I've been waiting for to talk about with terms of Cohen's D. Yes, I have a massive effect, but if I had a medium effect, if I even had confidence that I had a no effect, that, my confidence interval around the mean difference suggested that I did have some effect that was greater than 0. 0's not in the interval, right? But, I had a Cohen's D of 0.2, I would say, hey, doctors, do this. Doctors, be empathetic because being racist is really immoral and we need to go the extra mile to end our prejudice and stuff. I know that racism is a system and prejudice is like human behaviors and things like that. So I get it. But, I am human and I use those words when I'm speaking colloquially. I use them interchangeably. So I do understand the difference. It's fine. You can roast me on that. This is what I study. But no, nonetheless, I'll get off that. Everything worked out nicely. I'm going to try to pull this up here too. I don't think I can get everything in there. If I can get one, that's good. You can see we have our we have another check. We have 3 checks of our t-value. You don't have to do all of these. You don't even have to look at the t-value here. But I'm also saying, if you want, we have our t's, we have our p's here. You could use my hero's awesome program to just do this. I don't recommend it because I want you to get good at SPSS, and PSPP is helping you get good at SPSS. But, it all worked out. That's how you use PSPP. Alrighty, so let's use the t-distribution. All we'll be able to tell is if our p is less than 0.05, less than 0.10, or less than 0.01. So remember, we had 15 total participants minus 2. That's how you find degrees of freedom. I talked about that a lot. So that's 13. So if our T calculated score is greater than 2.161, we know that the p-value is less than 0.05. If our calculated value is 2.161 exactly, our p would equal 0.05. Ours is way bigger than that, so significant. But that's all we can statistically different. Excuse me. That's all we can really say. All right, so our graph maker has been updated. It is a little different. You got to enter in both your means, okay? You don't have to enter in your standard deviations. It doesn't matter in calculating these graphs or anything in here. So you enter in the standard error of the mean from SPSS or PSPP. Go ahead and make that clear. You don't want to do that one by hand, I'm telling you. N of group 1, N of group 2, all your labels. And then everything calculates for you, and you're like, hey, wait, why is the confidence interval negative? Well, it's just because of what group I put first. So if I really wanted to change everything, I could change everything, or you can just change the sign on every single score. You're like, negative 2.94 is positive 2.94. Well, actually, because you have to show the graph, you have to change it. So I'm just going to go, I'm going to copy that, paste it there. 0.5 is easier to remember than that number. You gotta give me a little slack, huh? And then I'm like 8, and then I'm like 7, and then I'm like control, and then I'm empathy, and then everything should be good. Yep, everything's good now. And everything's good now, right? So you do kind of got to check the outputs to make sure it fits everything else, But yeah, here we go. Here's our graphs. We plug and chug. We're 95% confident, that the true mean difference lies between 1.49 and 2.94 with our, with our estimated mean difference of being 2.21. That's the one we found. So we're 95% confident that the true population mean difference falls in this range. And all right, so now we get to write up our results. And I took that writing from Daniel Lackins and I converted it to what I needed. So Group 1 scored higher than Group 2, became participants assigned to the empathy intervention showed less racial bias and participants assigned to the control condition. If you notice, I took what he gave me and made it better, made it easily interpretable for my audience, and then I insert my statistics, my mean, my standard deviations, my T with degrees of freedom, my T score, my p-value, my 95% confidence interval, my Cohen's d, and a 95% confidence interval of my Cohen's d, which I will show you how to calculate, but that is very interesting. You don't have to include the 95% confidence interval of the Cohen's d. However, it makes life easier. I have a massive effect and a massive effect, right? Those are Cohen's d's. So my worst case scenario, it's a massive effect. My best case scenario, it's a massive effect. That's a little bit easier to interpret than my mean difference. My worst case scenario, my mean difference is 1.49. My best case scenario, my mean difference is 2.94, right? It's a little bit easier to interpret it when it's converted to a Cohen's d. Added to Lackins' effect size calculator, at least for us, is a lower limit and upper limit calculator of our 95% confidence interval of our Cohen's d. I just used math to make this work, but that's where the numbers came from. I'm going to leave this on the graph I upload for you. But right now I just added it down here. Just in case you want to use it, because it is a lot easier to interpret the 95% confidence interval of the mean difference when it's converted to Cohen's d's, right? It's super nice. It's massive and massive in this case, just like we saw in the example. All right, let's get started. We have a problem to do, and it'll be on the next slide. So today, I'm actually going to have you look at a manipulation created by my buddy Chris Rosick. Now, this is Chris, good friend of mine, actually. I love this guy. And that's me, and that's us doing at a science conference. having fun. This is Stoops and that's Amanda. They're both other friends of mine that have PhDs in psychology. But yeah, this is my buddy Chris, and he came up with something that I think is ground changing for you and your ability to handle stress in class. So what Chris has been looking at for a very long time is how to improve their grades in institutions like high schools and colleges. And he's particularly interested in solving gaps that are unfair. The intervention I'm going to show you here helped reduce the income gap in GPA, and I believe it was college students, might have been high school. He'll be mad at me for that, but that's okay. But he's done all this work reducing racial gaps in actual educational settings. He's a postdoc at Stanford. That means he has his PhD, and he's just building up a massive career of very impressive publications. I'm really proud of my buddy here. But he did something recently that I think will really help you out in your life. So what he did was he said, hey, what if it's not the stress that's the problem in test scores? What if it's the way we interpret or quote unquote appraise the stress? And Chris actually believes this, because I remember arguing with him about this when we were in grad school, but he believed that stress was good. And his argument, I was just like, I've had a lot of stress in my life and different things. I was like, Chris, you are the meanest dude I've ever met. He's not, but I was like, you are the meanest, most just mean dude if you think stress is good. I was like, you are wrong, brother. And then I would list all of the results I knew. We'd have a little war, and then we'd hug it out and we'd be done. But Chris is the kind of guy that if he has an idea, he's eventually going to test it in an experiment. And I love that about him. So his idea was that if we just view stress as an evolutionary adaptation that helps us survive, then, it's our stress response. It's not something to be avoided. It's something to be harnessed to do better performance. And so he took this idea and he created this intervention that has a control group and it has this reappraisal group. So I'm going to show you that right now because, one, your problem requires you to understand it. Two, it's going to help you out in life if stress hurts your test performance like it did mine in undergrad. I really think this would help me out if I could go back to undergrad. So here is the exact wording, and I know it's a bit of a read, so I'm going to read through it. As you might expect, taking a test can be a stressful experience. Before starting your exam, we are going to go through a procedure designed to help you perform at your best. First, please read over some information taken from a scientific journal article. The information is about how our body responds to stress helps your test performance today. After the reading, you will be asked to answer 2 questions about what you just read. This reading is based on Knox 2011 study in the Journal of Psychophysiology. Journal of Psychophysiology. That would just be a period. Chris is like me and likes typos. This is directly taken from his published work. So, haha, Chris, get a editor, buddy. Sometimes in important situations, people notice that they have a faster heartbeat, sweaty palms, shortness of breath, butterflies in their stomachs, and lots of energy running through their body. People usually think that this means that they are nervous, anxious, or worried. However, these feelings happen for all kinds of reasons, and it does not mean that we need to feel worried or nervous. For example, we feel the same way when we are excited about a surprise, when we are getting ready for a fun sports competition, or when we fall in love. So feeling a faster heartbeat, for example, doesn't mean you will perform badly. Having these feelings could actually help you. This is because when people care about something, such as doing well on a test, our body's nervous system tells the body to release energy and deliver more oxygen to the brain. This helps you to stay alert and pay attention to the important thing that is going on in your life. Therefore, experiencing a faster heartbeat, heavy breathing, or sweaty palms could actually be a good thing. It's your body's way of pumping you full of energy and attention. energy and attention. But it all depends on whether you choose to use this energy. As you are getting ready to take this test, just keep in mind that the feelings and symptoms you may be experiencing are normal. It is just your body's way of getting you prepared to tackle and deal with something important. Remember that the increase in energy you are experiencing is helping you, so take advantage of all that extra energy and attention. I mean, I think it's great. I'm not going to read the control. You can read it. I'll show you it. But what he did was he took this intervention and reduced gaps in GPA that are due to socioeconomic status, right? Money, class, whatever we want to call it, right? And this intervention worked but it works because it makes people not focus on the stress, not allow the stress to impact them as much. And he found that this really reduced that gap. So for me, what I think is important, anybody who's experiencing stress over tests or things like that, you are psychologists, just like my buddy Chris was. Don't be like I was in grad school. Be like Chris and say, hey, evolution created this process for a reason, to help me survive. Active control, it's a good control. Read it over if you want. It has words and a study in it. It's basically very similar to the previous one. Here are your results. And you have to convert these into all our statistics. So please go through all the steps. Get your results. It shouldn't take you that long. There's going to be a little bit of whatever. And I think that's great. Notice, don't put the scores in as A. I'm trying to trick you here, but I'm also going to explain this, right? A is a 4.0, an A minus is a 3.67, a B plus is a 3.33, an F is a 0.0, an A is a 4.0, an A is a 4.0. Right? Don't forget to run these data through the outlier detector. My guess is that 0 is an outlier in that condition, right? I didn't check it though. So check for outliers, remove them. In here, we got the active control. You can basically see what's going on here, but now I need the data. Okay, I need the p-values, need all the stuff. But essentially you're going to have one row per participant. Participant 1 is in reappraisal condition. So with convention, that'd be their participant 1 in condition 2, and the first person, their score was a 4.0. So participant 2, condition 2, score 3.67. Right? So that's just kind of how you fill it out. And then you get your SPSS, you plug and chug stuff in the Cohen's D calculator. You can do all the stuff you need to do to get the information that you need. When I say SPSS, I mean the low quality GI Joe program, PSPP. Now you're getting some insight into my life. Yes, I did get a lot of cheap, non-authentic GI Joes, and I would blow them up with firecrackers. Mwah. Okay, but this is your problem. You can solve it. Okay, I'm putting it up late. I'd like you to try. Okay, it's okay if you try. Try to get this problem done. If you need an extension, let me know in class and I'll grant you a little extension, but really I think you can get this done in a few minutes. Maybe 20 minutes. But that's it. Solve it, y'all. Thank you again for being my favorite class ever.